Hello everybody, this is Eric Pistelli from Antico, and in this video we're going to analyze a complex malware, an office malware, which I didn't choose for any particular reason. Actually, it was linked to me by a friend of mine just because it was a fresh sample, so there's no particular reason why I chose this. It's, as I mentioned, an office malware, and it has multiple stages. So we start by analyzing the file. This is the office file. And if we look at it, it's a zip file, so it's a newer Office file. It contains VBA code, so if we click on that, we can inspect the code. Now we can already see that the VBA code is obfuscated, so it's kind of hard to read, but you still can understand it because the obfuscation is not that bad. So if you look closely at it, it constructs a JavaScript file name, and it writes it to disk. If you look at it, the first thing which pops out from this VBA code is actually the use of file system object, and we can see it creates a text file and it writes something to it, and then it closes it. Now what it writes is this variable, and this variable, if we look at the beginning of this function, is this one, and if we look where this function is being called, it's here. And if we check what the second parameter is, the second parameter is actually being assigned here, and this means it assigns to it the value of this text box. Now after it wrote to it, it calls end file run, and it runs the file. So what we need basically to understand what it writes to disk is the content of this text box, and this is actually contained in the VBA project itself. So if we go to the user form, it's actually in this blob of data, this data blob, and we can see this is the JavaScript. So let me select the JavaScript and I'll dump it to disk. It goes till the end basically. So if I copy it to disk, I could have also just, to be honest, copied to ASCII or even ran this action bytes to text, so I can directly do this, and I can select JavaScript as language, and after that I can just right now it's basically all in one line, so we can beautify this just to make it a bit more readable. And at this point, what we get is a very obfuscated JavaScript. This is very difficult to read. So what we'll do in this video is I'm going to explain how to deobfuscate this JavaScript in stages. Because if you ever encounter obfuscated JavaScript and you don't have a deobfuscator for it, you'll have to do it by hand. And anyway, it's kind of tricky using some obfuscator, because if something's wrong in the obfuscator, it could actually output the wrong code and you could miss an important part. So by doing it in stages, you can see the difference between the previous stage and the next stage and check if anything has gone wrong. So if we analyze this JavaScript, the first thing we can see is that it uses this b function and then a number in it, or at least a string number. And if we look at that, we can see here this function, which basically what it does, it takes this huge array basically and it solves the strings from it. So what we'll do, we'll try to resolve the string using that b function. We will not use Python for this, we will actually use JavaScript, and we will just import the b function itself and let it resolve strings for us. We will not do it ourselves. So let us open a new JavaScript editor and let me load the first stage. So what I did is basically this. since JavaScript in Cerbero doesn't have access to the UI, it's contained, it's in a sandbox, and this is on purpose. So how to actually analyze some JavaScript? What I did is I took all this text, or you can take it from the here from the hex viewer itself, but if you don't have a hex view open, what you can do is you can run the action and do sorry, wrong view. So you can do basically text to bytes, and then afterwards you can use a filter to encode it to base 64. And at this point, what you can do, you can copy it to ASCII, and if we open a new JavaScript editor, we can do, and at this point, using the A to B function to decode the base 64. And at this point we have this string script on which we can do all the transformations we need. So this is exactly what I did in the first stage of the deobfuscation. So basically, here we can see we have this A array, and then also we have this B function which we'll use to decode the strings, not all of them, but some of them. And this will make it much more readable. Here we can see the script and the A to B function like I explained before. And at this point, what it'll do is it will search for all occurrences of B being called, and it will get the index, and it will call the B function with that index and replace the result, the call with the result of calling the B function. And afterwards it will just remove the B function and this huge array in the beginning because we don't need it anymore. So if we execute it, let me put the output window here so it's better visible. And the view, we don't need the word wrap. So this is the result of our script. If we select it and cut it, this we can close. And at this point, let's open a new JavaScript editor, just because we have already the highlighting. And now, if you look at it, what you'll notice is that we don't have any more calls to the B function. We'll actually see strings being resolved. And at this point, we have already also some of the strings visible as links, for instance. And we could guess that one of these links is actually the one being used to download malware. But before going into that, I want to continue with the JavaScript deobfuscation, because this is for educational purposes and it makes sense to dig a bit further into it because it's interesting. One thing which I forgot to mention is that, of course, you can also try and debug this script, but you will, of course, miss some functions, some functionalities. This is a JavaScript for the JScript interpreter by Microsoft. It has access to an API of the system, which is not present, of course, in the debugger. And you can, of course, provide this API as a fake stubs and then debug, of course. But still, even in a debugger, it's kind of hard to read in this obfuscated JavaScript. So it does make sense to try and deobfuscate it at least a little bit. And as you can see, it's already much easier to read this. So the second stage in deobfuscation would be to get rid of, if you look at a function, what it has at the beginning. Every function has a big, a huge, or not always huge, but a dictionary filled with strings. It's a key value, of course, dictionary, and it has sometimes strings and it sometimes has functions, very simple functions. And what it does is it in the code, instead of using a string directly, what it does, it uses the dictionary and retrieves the value from the dictionary. And this makes the code a bit difficult to read, because you will have this kind of syntax. For instance, if we look at this EI dictionary, we'll see that this index is basically this function, which does nothing else than take another value of another dictionary and then use these two parameters as parameters for this function. So it becomes kind of hard to follow, of course. At this, in fact, this particular function is nothing else than this comparison, basically. So you have even nested dictionaries, or let's say the use of nested dictionaries. So you have one function containing another function, and both functions have a dictionary, and the innest, or let's say most inner dictionary references the outer one. And so following this becomes kind of hard. So the second stage in our deobfuscator will be to remove this kind of switch, not switch statements, but dictionaries. And if we look at the code, what it does is find these kind of dictionaries and extract. What it does is it actually evaluates the dictionary itself and takes the value from it when found in the code. It skips the declaration of the dictionary in the clean script which we're creating, and then it basically replaces all the values by using the same index. So when it takes this, it finds this dictionary, it extracts it, it evaluates it as JavaScript, so we have the dictionary in our code ourselves, and then every time it finds an occurrences of EA, for instance, it takes the index and resolves the value and replaces it with the string representation of that value. So if we execute this, now, at this point, we don't have any more these dictionaries, and you can see it's already much easier to read the code. What we still have, though, is the use of these fake functions, which do nothing else than, let's say, an addition, a comparison, and so on. We have very simple function calls all around the code, because what we did before was just to get rid of the dictionary. So at this point, we still have, for instance, this function does nothing else than calling these, the LA function with the LB and LC parameters. We can get rid, of course, of these functions. They are completely useless, and they make the code hard to read. And the easiest way to actually get rid of these functions is by using regular expressions. So if you don't know regular expressions, I suggest you learn them, because they're very useful, especially when you have to do these kind of modifications. In fact, there are various types of these kind of functions throughout the code, and as you can see, there's basically 6 of them, 6 of different types of these functions, and I constructed a generic regular expression, and I just replaced the parts which differ, and doing this without regular expressions would be much more difficult. This is all the code of the third stage, the whole code. So you can see it's very simple. Another thing that I do in this third stage is getting rid of the occurrences of this, for instance. This exclamation, twice exclamation mark, and then square brackets, open close, is means true. And if it's just one exclamation mark, it means false. So this is another regular expression to get rid of these. It takes into account that there could be spaces between the exclamation marks and the square brackets. And in fact, in the code, we have times where there are no spaces and times where there are spaces. For instance, here there is no space, and this just means false. So it's a simple replace of these expressions. So we run the third stage. And we extract now the result value from the script, delete the rest. Now at this point, you can see we still have some of these simpler functions around, because some of them had arguments which were too complex to fit in a regular expression easily, but still most of them are gone, and we have now simple comparisons all around the code like these ones. And we can see already that there is a lot of garbage code which will never be executed, and it makes it easier for us to read and skip over that part of the code. There's still something which is quite difficult to read in our code, and these are the switch statements. Basically, if we look, here's one for instance, all around the code we find switch statements which contain, which are preceded by some kind of string with some indexes, and this string is split by this separator character. So we obtain basically an array of these indexes, and what it does is it executes these case statements in a while. Once the index is bigger than the size of the array, the while will actually stop, because we reach a break statement, because it doesn't match any case. And so basically these are like instructions but out of order, and it uses this array to recreate the order. So it executes the instructions in the original order by using this index. So this is just a way to shuffle instructions in the code. This is done by the obfuscator. So what we have to do is basically find the occurrences of this string, and then parse correctly the switch statement, or let's say find whenever a case begins and ends, and put them again in order, and remove this whole while switch logic, because the whole idea is just that we take the instructions in order. So basically here we have a 10, so it means that we go to case 10, this is the first instruction, we just take this code and we put that at the beginning of the if statement, removing all the rest, and the second one will be 23, so we go to 23 and we take this, and this will be the second instruction, and so on. So that's the whole thing that we're doing in the fourth stage. So we load the fourth stage, and as you can see, the code of this is actually more complex, because there are also nested switch statements which make it harder to parse. For instance, in this case we have, as you can see, a nested switch statement. We can rely on the fact that our beautifier put a certain indentation level to the switch case, and we can rely on that to actually construct our first stage, the obfuscator. We'll take the indentation into consideration to make sure that we are actually finding the right case. So we execute the fourth stage. Again, we extract the value, the result value. And now you can see we have already a much easier to read code. Of course, a lot of it is just garbage, but in between the garbage we can see real instructions being called. And so this is actually much easier to follow than before. The last stage we're going to perform is about some of the strings which are here used. You can see, for instance, open, position, close, and so on, and these are being used in specific parts of the code. For instance, here we can see it used this particular string in this particular part of the code, and it doesn't make sense to have them as variables. We can directly replace these occurrences of strings in the code, and it will make our code much easier to read. So this is actually gonna be an easier stage. It's not very difficult. So what it does, it finds these variables. I'm just replacing the ones which are at the root level of the code, basically. So these ones and not the ones in the functions, because the ones which are at the root level are the ones which are the most interesting. So that's what I'm doing. I don't want to make it too complex. And what it does, it finds these variables, and then first it collects them all, and then simply replaces all occurrences in the code, again using a regular expression, sorry, which matches only whole words. By using this b escape, it matches only whole words. So again, it finds all these occurrences, extracts the variable name and then also the value, and it pushes them to an array, and then it just goes through that array and replaces them in the script. Very simple. So we run the script, we extract the code, and at this point we have something which is much more readable than before. As you can see, we can already follow a bit the code logic, in a sense that we can see use of APIs, use of the URLs, and at a certain point also use of the logic to download these files. And basically, if we look at the script, it's quite apparent that what it does, it uses one of these URLs to download the file, save it to disk, and then run it. I mean, we could go on and clear out the garbage, but we have already an idea of what the script does, and we won't go into cleaning up also the garbage, because I think it's already readable enough for us, for our purposes. So what I did yesterday is to try some of these links out to download the file, and the only one which worked, or let's say I didn't try all of them, but I tried 3 of them, and third time was a charm, because this one worked. So what I'm gonna do now is using this this URL download action, which basically what it does, it downloads over torrent. Now, as you can see, I started this torrent browser, and so I can use this action to download stuff over torrent. I don't want my real IP to leak. So it uses our URL, which we have just selected, and let's see if it still works today. Great. We have now the downloaded executable. So let's now open this executable. As we can see, what it does, it downloads this executable which mimics an antivirus updater. I don't know what that should be, but apparently it's good enough, from AVG. Of course, this is completely bogus. If we look at the file itself, it's also not much of code. I will show you in a moment. We'll open it in Ghidra. Even by looking in Carbon, we can see it's not much code, and the analysis took very little to perform. So of course, there's something hidden here. And let's open Ghidra. Oh, I have it already open. Wait. Yeah. Let's analyze the file. Yeah, we don't have PDB information. So I'll open the interface here in Cerbero because I'm used to it. And if we start looking at the code, what it is that it looks like some very, how can I say, unsuspicious code. It does some window operation, typical of a hello world window, like when you create in Visual C++, some hello world window application. It looks like that. It's probably, they took probably that application and just modified some parts of it. And this is obviously made to fool antiviruses. This, as we can see from the parameters, is the WinMain. And here we can see it constructs this window, which is completely bogus, of course. The function which we actually are interested in is this one, and we can call it real code. And even here, there's a lot of code which is not interesting to us, but one thing is interesting here, and this is not here, but this function. Here we can see it does a virtual alloc, and let's rename this variable like allocated memory. Now, and here it sets some pointer to the allocated memory, and just from the look of it, I can already tell that it is an entry point to some code, because once you do virtual alloc, and again, this 40 flag represents basically page read write execute, so it has executable privileges. What it will do is for sure to copy some code there and to execute it. So what we do here is code entry point, and this is the size. call this alloc memory. And at this point, we have a memory allocation, and as you can see, it performs then some operations on the allocated memory, and afterwards it calls this code entry point. So basically what it does is it allocates memory, it copies and decrypts some data into it. We can see somewhere here it decrypts the data. Yeah, this should be the decryption function. And afterwards it just calls the entry point into that allocated memory. So without going into reverse engineering the algorithm itself, what we do is we take a debugger and we set an entry point. First we set an entry point here after, or let's say at virtual alloc, just to know where our memory is being allocated. And afterwards we just set an breakpoint here before code execution, of course, just to dump the memory on disk, and then we can analyze it further. So that's what I'm going to do. Let me copy this here. Of course, make sure you do this in a VM, because you don't want to infect your actual computer. And make sure to make a snapshot. And just to make sure, if you want to make sure that nothing happens, you can even knock this part of the code. If you want to do this, you can open, for instance, the file in Carbon and go on this instruction, just select it and open the hex editor from there. It's easy to patch. Or you can do it in the debugger, it doesn't matter. So as you can see, I renamed it to X and it mimics the AVG icon. We'll open this in OllyDebug. So at this point, what we need is first the address of this. So we'll put here 1, and afterwards we need the address of this jump, and we'll put another breakpoint right here. So now we'll get to this call to virtual alloc. We can just step over this, and at this point in AIX we'll have the address of the memory being allocated by the malware, and we can then just continue the execution until the jump. Right, now we have the jump. Of course, now we stop the execution. What I do, at least, I could dump in OllyDebug. What I do is I usually use Task Explorer just because I'm used to. And you can use any tool you want, of course. So what I do is I dump the region. It was 4C. So this is the, as you can see, it has page execute read write access, and we can just dump this. Let's call it malware shellcode. And at this point, this is done. Okay, we can stop the analysis of the downloaded malware because it doesn't do anything else. It just executes this shellcode, let's say, and we can close this. At this point, we can also eliminate this one. So at this point, we have this malware shellcode. Let's open this one in Ghidra as well. Before opening in Ghidra, let me show you something in Cerbero. If we look at the, okay, it already detects some shellcode. We can create a new Carbon database for it. Let's make it, yeah, it's x86, of course, and we have to start the analysis, of course, at the entry point, which is good because I forgot to actually wait a moment. Let me first select here the correct x86. So anyway, it's x86 32-bit Visual Studio. Yeah, so looks about right. Okay, this doesn't really matter. The only thing was we have to go to the entry point and then start the analysis from there. Ghidra will actually try to identify the code by itself, so you will not have to set the start of the code yourself. So analyze it. Okay, it didn't take long. We can open this again in our UI, and as you can see, there's not many functions here either. It's just actually we can look at them in the decompiler because most of them are small. Just a handful of them is larger in size, and as you can see from the stack, you can see that it pushes some strings on the stack. And first, to understand this, what this does, this wait, let me also put here this was the entry point. So this is the entry point. We can even call it entry point, and we can mark it as entry point. At this point, what I wanted to say is, okay, this is the entry point from the shellcode. Here it does some stuff, and starting to understand what it does is we need to understand what these strings on the stack mean. So what I did basically is I wrote a small Python script to do this. This is a generic script to interpret a string on the stack. In the future, I'll make it easier to execute because it will have access to the disassembly itself. But here we limit ourselves to basically copy and paste. It's not a big problem because there aren't many of these functions with these stack strings around. So, but anyway, these are two strings, for instance. So what we'll do is we start commenting them just to have an idea. Of course, the second string starts after the 0. So let's find all of the functions which have this kind of strings. We'll just put here the code and we'll comment it out here. This we did already. This is another one. sorry, forgot to. It's a virtual free. So we can already start understanding in which direction this all is going, but let us finish this. And I do remember there was another one, another place. But I think it was nested in another function. Probably this one, yeah. Yeah, here was another one. Although these strings seem kind of bogus, to be honest. Yeah, this seems bogus. But anyway, we have already commented some of these, and actually all of the important ones. So we go back now to the entry point, because now we can better understand what this all does. So if we look at this function, what it seems to do is to get a base for kernel 62. And if we look, for instance, at this function, it seems to call virtual alloc. And if you can see here, at a certain point we have some XOR and some operation on some memory which is being allocated. So, for instance, let's say this is virtual alloc. Here it gets the base of kernel 32, because if you look at these characters, it's a K. This, I can already tell you, is a uppercase K. This is an E, and then there's an R. And so it checks it is either lowercase or uppercase. So basically it finds the base of kernel 32. So we can, wait a second, yeah. So we can comment this as get kernel 32. Then here, as you can see, there's a get proc address, and what it does here is just a string comparison. So basically it, even though I didn't step into the code, I can guess this is some iteration over the export table trying to find the address of get proc address. And at this point, it sets getproc address API in this variable, and it calls getproc address with uvar1, which we already established as kernel 32, and with local 1c, which is virtual alloc. So it resolves this virtual alloc API, and it sets the result in local c. It then calls local c with these parameters, and after this call, basically, which we will call alloc memory, at this point we have memory allocation in local 80. If we look at local 80, what it does on local 80, it seems to copy memory and then basically performing this XOR operation and so on. So after these two functions, we will have some memory decrypted, allocated, and then copied, decrypted. And this function, so I'll call this decrypt code, and this function is interesting because if we look into it, just from experience I can tell by looking at the numbers that it's going to load some. This, for instance, is, if I'm not mistaken, ILFA knew the value in the DOS header. So this is actually, it seems to be mapping a portable executable in memory. But we're not much interested into this, because what we want to do is we want to obtain the decrypted executable in memory. So what we'll do is we'll put a breakpoint right here to decrypt code, and after decrypt code we have the value of the memory position of the allocated memory in this parameter, and the size should be this one, and but the size is not very important because we will of course dump the whole region, and we need only the start of the memory. So this is the important part. So what we'll do is we'll execute this shellcode, and we'll, up to this point, up to this decrypt code function. So what we'll do is we open this shellcode in Cerbero. We of course need, we cannot just execute the shellcode, we need to put it into an executable. So what we do, we select all the data, and we run this action, shellcode to executable, and it already asks us, well, it asks us which kind of architecture. In this case it's x86, so that's what we're gonna select, and we have to take care of the entry point, because the entry point is not the first instruction. So we have to go and put, let me go to the start of the, this is the entry point, this number. So let's go back here, and we set the entry point to this. This is very important, otherwise we won't have the correct entry point. Okay, now we can execute, and we're at the shellcode, which, and we have to, it's mapped at 004010000. So we have to take into account that extra, okay, of course the initial 4, but also the 1000 offset, which it is being mapped at. So again, we go to the decrypt code, and let's go to that position, but we have to take into account the extra 0040. So it would be this one, and at this point we should have this decrypt code, and it should match the push AX, yes, malv push ADX, exactly. Here we have our decrypt code, and it is being followed, of course, by this, I didn't name it, but this is, let's call it load PE. So this is our load PE function. Now we can execute up until this point, and at this point we have also the memory address, of course. In this case it's this 00200, and we have to step over this function. Right. Now what we'll do is we, of course, dump the region. Again, I'll use this application. And we go here. As you can see, it's already in the beginning, this page execute write. And we dump it. And I call it just malware mapped. Okay, at this point, we can close this because it doesn't do anything else than execute the mapped portable executable. And we'll load this into Ghidra as well. Let me close these ones. And let's start the analysis of this one. So as we can see, if we look at it even in Cerbero, it is a normal PE, but it has something which is strange. It does have only one import in kernel 32. So this is actually one thing which is strange. And let's look at it in Ghidra. Yeah, it doesn't have a PDB. All right, now let's look at the entry point. So the first thing you're gonna notice is that it seems to have the whole code because Ghidra disassembled all the functions, but it doesn't have the imports. So it has to resolve the imports, of course, in some way, because there's no packer apparently, and there must be some way in which it calls the imports. So just by looking at the entry point, if we go into the first function, we can see something quite strange. A lot of local variables being used with something with huge numbers. And if you have any experience into this, you probably are going to think that this is going to be hashes for APIs. And you're right about this. This is a way in which it solves the APIs. In fact, it calls one function which, just by looking at what it does, it seems to be resolving a particular module using a hash function. This is the hash function. And once it finds the module in memory, what it does is it is going to resolve the whole array of imports. So we can call this resolve imports. But if you go into the second function, we can see it does the same basically. It has this huge array and a find module, and then the function to resolve the imports. So we can call this function resolve imports too. And at this point, after these two functions being called, we have all the imports resolved. So let's open this in the debugger and step over these two functions, and let's see what happens, because this is interesting. Call it X. Let's open Oli debug. Wasn't Oli debug, awesome. So we're going to open this executable, and now we're at the entry point, and these are the two functions we've just analyzed. And if we step over them, let's look at what happens, because this is interesting. I'm now stepping over stuff, and I'm stepping over the first one. Look at what happens. Huh? I can already see one API being resolved. So the first function actually resolves NTDLL APIs. And if I step over the second function, I can see all kernel 32 APIs being resolved. Now at this point, we have all the import address, well, we have the whole import address table already being reconstructed in memory. And this brings us back to like when I was in my youth and dumping stuff and rebuilding the import address table, or let's say the import table, because the import address table is already intact right now. I tried to use imprec to fix it, but it didn't work. So what I used is chimprec, and let's try this one. Okay, there's a small issue, and it probably has to do with the fact that I had this also an issue with imprec. They don't handle correctly the fact that it's a relocatable executable. So because at that time it was over 10 years ago, they were not common, and I don't know, in imprec, probably when imprec was done, they weren't even existing. I mean, DLL could move, but executables didn't, so ISLR wasn't a thing. And what we do is something very simple. We close this, and we change, well, we remove the relocation, the base relocation from, oh no, actually we can, sorry, this can be much easier. We just remove the flag from the DLL characteristics. DLL can move. If you want to make it also cleaner, you can even remove the base relocation from there, and it will remove also the directory, but this is enough, to be honest. So at this point, we open Olly debug again, and we open our executable again. I actually wanted to remove this relocation before. I just forgot about it, but it's nice so you can see the problems you can encounter when you actually don't do it. I didn't, again, test it with chimprec, but imprec had the same issue. So we go to the entry point, and again we step over the two functions which resolve the imports, and now we have the imports. And at this point we open again chimprec, and okay, this may be not the issue, maybe it's just the fact that I didn't run it as an administrator. So let's try open it as administrator. No, doesn't work. So why did it work yesterday? This is interesting. So doesn't seem to be working chimprec, and nor does imprec, that I knew already yesterday. I don't know why chimprec is not working today. It worked yesterday. So what I ended up doing is using Shilla, another import reconstructor. And what we do is we select, of course, our executable, and we do the yat auto search, and it finds the correct address of the import address table and also the size. So we do get imports, and it finds all our imports. So we dump the file. Let's do a p rebuild on it, and let's fix the dump with. Now at this point, let's rename this one as fixed, and we can delete this one. So at this point, the backup we don't need. At this point, we hopefully, when loading in Ghidra, we can see our imports. It's already still loading the file, but we can already open it. And as you can see, we finally have our APIs visible At this point, analyzing the executable with the help, of course, of a debugger maybe, or and with using either Ghidra or IDA or whatever you're using becomes much easier. We can see in the decompiler now all the resolved APIs, like the library and so on. So at this point, I would say this is analyzing the Trojan itself, of course, or whatever this is beyond the scope of the video. But I think we covered a lot of ground here. We went from an Office document and then VBA code. VBA code extracts JScript code on disk, runs it. JScript code, we deobfuscated it. Then we extracted the URLs using to download the file and execute it. And from there, we had some shellcode being decrypted and executed. And the shellcode maps some other portable executable into memory. And after that, we rebuilt the import table of that executable in order to analyze it in a disassembler decompiler. So I hope you liked it, I hope you enjoyed it, and till the next time.